In this video, I'd like to start chapter 7 and start tying some of these energy ideas together. So our picture of energy right now has a couple different pieces to it. We can move energy around with work, and energy can exist in these different forms, right? We have our kinetic energy, and we have our spring potential energy, and we have our gravitational potential energy, and we have equations for all of these. These are definitely ones that are good to know. So like I said, energy can move between these different forms by doing work. The work energy theorem tells us how network changes the kinetic energy of an object. And all of the forces associated with these types of energy, these are conservative forces, which I've mentioned before in videos. So this means that the force of a spring and the force of gravity conserve energy. Now, normal force and tension, well, I should say normal force can't really do work in this class, so it's not going to be involved in energy. Tension can do work, but only if it's, only if something else is pulling on the other end of the string and doing work. The tension can't store energy, it can only transfer energy. So I guess the way of saying that is tension conserves energy, but because there's no potential energy of tension, there's no energy stored in the string, we don't have to worry about it as much in this picture. But there is another important force that we haven't talked about, friction, right? And friction does not conserve mechanical energy in the same way as these other things. In other words, friction does not have a potential energy associated with it. If we put energy into friction, we don't get that energy back. That energy is lost in the form of heat, right? So when we say friction doesn't conserve energy, we don't mean that friction makes energy disappear from the universe. What we mean is that in the context of this mechanical energy, springs, gravity, kinetic energy, friction can make energy disappear from that picture. And in real life, we know that energy has gone into the thermal energy of those objects. It's heated the temperature of our block's surface up by a couple degrees or something like that, and that makes that energy a lot harder to see in the lab, but it still exists in the universe. So when I'm going to say things don't conserve energy, that doesn't mean big picture not conserved. That means they don't conserve our mechanical energy. So friction, I just have to give that disclaimer or else people will think that energy is not conserved in the universe. Okay, friction does not conserve mechanical energy. And because of this, we say that friction is a non-conservative force. It does not conserve energy the same way that springs and gravity do. Okay, and what we say when we mean mechanical energy is exactly these things. Our different forms of energy that we've learned how to account for. What all of this means is that if there are no non-conservative forces, then the total amount of energy in our system has to stay the same. It has to stay as this mechanical energy spread out between some combination of kinetic and potential energy of the spring and gravity. So if we were to write down a statement for this, it would be the following. If we have no non-conservative forces, then our mechanical energy is constant, which is to say we can write mechanical energy in a couple different ways here. But one way I like to write this is that the change in the kinetic energy plus the change in the potential energy, and this could include spring and or gravitational energy, is equal to 0. So the total change in energy of our system has to be equal to 0. I'm going to put a box around this. We can also rewrite this. So delta K is K final minus K initial. Delta U is U final minus U initial. And if we add these initials to the other side and leave the finals on the other side, we get K final plus U final equals K initial plus U initial. And I think this is kind of an easier equation in some ways to see what's going on, right? The initial kinetic energy and the initial potential energy, this is just all of the energy we start with in our system. K final and U final, this is all of the final mechanical energy that we end up with in our system, right? So the amount we start with has to equal the amount we end up with, as long as there are no non-conservative forces that take away this mechanical energy and, in the case of friction, turn it into heat. All right, so this is super useful for solving equations, and let's just do one quick example right now. So here's an example. Let's say we have a ramp that we are launching a little toy car up. So this car has a spring that is compressed next to it, and it's starting with an initial velocity of 0, but this spring is compressed a distance of 10 centimeters, and this cart is shot. So the spring is let to expand. It pushes on the car accelerates, and the car ends up here at the top of the ramp, a distance of 3 meters away, and it has a velocity of 5 meters per second. So we would like to find the spring constant, K, lowercase k, of the compressed spring. Okay, so this is a pretty complicated place to start, but I think this will give everyone a chance to see all the pieces in action. One last piece: this is frictionless, so again, there are no non-conservative forces, and we can use our energy conservation equation. Okay, so let's do a little accounting of the energy. So our kinetic energy, delta K, that is equal to K final minus K initial. These are, again, capital Ks. This is our kinetic energy. So K final, there's a piece of information we're missing. Apologies. The mass of the cart equals 0.5 kilograms, so 500 grams. Okay, sorry about that. So the final kinetic energy of the cart is 1/2 mv squared. So m is 0.5, v is 5. And the initial kinetic energy of the cart is 0. So this is easy. Our changing kinetic energy is 1/2 times 0.5 times 5 squared, which equals 6.25 joules of energy. So this is our changing kinetic energy from start to finish. The cart gains 6.25 joules. Our our potential energy has different parts to it, right? So our total potential energy has a spring, and we also have to worry about gravity. So delta U is equal to the spring part of that plus the gravity part of that. So the spring, let's think about the spring. So this is the final state of the spring minus the initial state of the spring. Well, the final state of the spring is, once it's done pushing on the cart, it is back to its equilibrium length. Nothing else is pushing on it. So this final potential energy must be equal to 0. And the initial potential energy of the spring, well, that is what we would like to find out, because if we know how far it's compressed and we know the energy, then we can calculate what the spring constant is, because US is equal to 1/2 K delta X squared, and we will know delta X and we will know US. So this is what we would like to find. All right. delta UG, for this, the initial gravitational potential energy, we can say that this thing starts at a height of 0, and it ends up here, some amount higher, with potential energy mg y final. So, let's see, I can erase some of this. So we have a triangle that looks like this. 3 meters, 20 degrees, and we want to know y final over there. So that is just 3 times the sine of 20. So mgy final is equal to 0.5 times 9.8 times the height, which again is 3 times the sine of 20. And plugging those into my calculator, I get 5.03 joules of potential energy. So delta UG is 5.03 minus 0, so this is equal to 5.03, that's positive 5.03 joules. Okay, we're getting towards the end here. This is good. So I'm going to erase this. So our delta U was equal to the spring, excuse me, this is equal to the change in the potential energy of the spring, which is minus US initial, plus the change in potential energy of gravity, which is plus 5.03 joules. So this is delta US, this is delta UG. And now we are almost done because I can erase this, because we know that delta U plus delta K is equal to 0, right? This is what we said because mechanical energy is conserved in this problem. So this is awesome. Now we can, we know that this is equal to minus U of the spring initial plus 5.03 plus delta K, which is 6.25, and that is equal to 0. So moving USI onto the other side, and moving USI onto the other side, we get 5.03 plus 6.25 is equal to USI, which equals 11.28 joules of energy that started in the spring. So this, of course, is equal to 1/2 K delta X squared. So 11.28 joules is equal to 1/2 times K times 10 centimeters is 0.1 squared. So solving this, multiply both sides by 2, divide by 0.1 squared, and that gives us that K is equal to, and this is a pretty stiff little spring, 2,260 newtons per meter. So to recap there, we figured out where all the energy was, or how all these pieces of energy changed. There was only one piece of that we didn't know, which was how much energy we started with in the spring, solved for that energy, and then used that energy to solve for the spring constant K. Conceptually, there is another way to think about this problem. So rather than thinking about these changes in the kinetic and potential energy, we can use the other rearranged equation, and I won't do it, but we'll give you the quick outline of it. That was U final plus K final equals, I guess maybe that was backwards. K final plus U final equals K initial plus U initial. And each of these U's is split into multiple pieces, right? So this is really K initial plus U spring initial plus U gravity initial. And this is K final plus U spring final plus U gravity final. These don't really line up right. But now, like, this is all of our energy in the beginning, all the different places our energy can be. This is all the energy at the end, all the different places our energy can be at the end. And now a bunch of these are zero, so we can just start plugging in zero. Like in the initial state, the cart is at the bottom of the ramp, so this the gravitational potential energy is equal to zero. The cart is also stopped. Later on, the cart is moving and it has some gravitational potential energy, but the spring is not compressed anymore. It's at its equilibrium length. So rewriting that, we get K final plus UG final equals USI, and you'll see these are exactly the pieces that we had before. This is 6.25 joules plus 5.03 joules equals the unknown thing we're looking for, which was 11.28 joules. So whichever one of these two ways of thinking about the problem is great. It seems like students are pretty much split 50-50. If I'm doing problems on my own, I tend to prefer this second way. But again, that's just, the habits, the way you learn to think about these problems. So yeah, whichever way makes sense to you is the right way to deal with these problems. The next thing we're going to learn is how to deal with things when we do have non-conservative forces.